Space, the final frontier. For some 60 years now, we've been skimming the stars and sending robots and astronauts up into orbit and beyond. But we've always used rockets, and they are rubbish. Eye-wateringly expensive, almost always wasted after one shot, dangerous, unreliable, polluting, and because it takes a lot of fuel to get into space, and more fuel to get that fuel into space, really inefficient. Surely there must be a better way. Well, actually, there are several. Here's our top 5 ways of getting into space that they've actually tried. Skylon is far more than just a CGI dream. It's actually pretty close to flying. This vast Thunderbird-esque plane is a rocket-jet hybrid. It takes off like a normal plane, flies into space, delivers a cargo of up to 11 tons to the ISS or other stations, then flies home to land, refuel and take off again. The secret to Skylon is the Sabre engine. Most planes have big heavy engines which operate at limited power to control their temperature. Skylon doesn't. An innovative cooling system in the nose freezes air from 1,000 degrees Celsius down to minus 150 Celsius, where it's burned with an onboard hydrogen fuel, allowing the engine to be lighter and run at far higher loads. It accelerates to 5.4 times the speed of sound at 16 miles high. Once there, it shuts off the now very thin exterior air supply and uses onboard oxygen to rocket the plane into orbit. If it works, it'll be seriously cheap to mass produce, cheap to run, very efficient, using less than a fifth of the fuel of a comparable rocket, and it should be very reliable. And it's being built. The engine pre-cooler, by far the most difficult part of the project, works and has been signed off by the ESA, freeing up millions of pounds in European and British funding. Millions isn't nearly enough though. If they get the probably billions they need, Skylon could be flying within just a few years. To get into space, you need thrust. But what if you had a way of beaming thrust from the ground rather than creating it from fuel carried on board? A much lighter and therefore cheaper and more efficient ship. That's what. Light craft have a special mirror on their underside which focuses laser light beamed from the ground to a point in the air directly beneath the craft. The air is heated to 50,000 degrees Celsius, 10 times hotter than the surface of the sun, and explodes. The shockwave pushes the ship up. All the way back in 2000, a group of private and government bodies used a 10 kilowatt laser to lift a 1.8 ounce ship 233 feet off the ground. It's estimated that with a 100 megawatt laser and a 1.4 metre mirror, supply and satellite payloads of up to 100 kilos could be sent rapidly and very cheaply to the International Space Station and other platforms. Most of the problem with getting things into space is that it takes loads of fuel, partly because a rocket needs to be going really fast to escape the Earth's gravitational pull, and partly because fuel is heavy and needs even more fuel to lift it up. So how about a system that gets you into space very slowly and picks up all its fuel en route? Enter the space elevator, which does exactly what it says on the tin. A cable up into an orbital platform upon which ships and satellites can be lifted and sent off on their way using only the tiniest amounts of fuel. Either the cable can be electrified to provide power, or it can be transmitted from the ground via lasers, which overcomes several engineering problems. There are still many problems though. To work, the cable would have to stay in the same position over Earth. That means that the platform end has to be in geostationary orbit, some 36,000 kilometers from the surface. Then, to try and make sure the lift car doesn't bring the whole system crashing down with its weight, the cable has to extend further, twice as far in fact, to act as a counterweight at the other end. But the main problem is that cable. At least 36,000 kilometers of it, which has to be strong enough to take its own weight and the force of the counterweight, car and cargo, and flexible enough to withstand weather conditions en route. That's no mean feat. In fact, until recently, there were no materials which fitted the bill. Carbon nanotubes show promise, being extremely light, strong and flexible, but as yet, no one can produce nearly long enough strands of them. The system does have its champions though. Japan holds regular space elevator competitions and has pledged to be a leader in any future scheme. To space on nuclear bombs. Sounds like dodgy 1950s sci-fi? Well, check this out. the Department of Energy actually tried it. It was called Project Orion. The idea was simple. A ship dropped a bomb behind it, the bomb exploded, and the ship rode the shockwave, potentially reaching speeds that would put Saturn and possibly even Neptune, Pluto and beyond within reach of astronauts. The theory was sound, as you can see from these early tests, which used conventional explosives. The real thing would have been vast, several times the size of a Saturn V rocket for a long trip, and weighing up to 10,000 tons. 800 bombs weighing anything from hundreds to thousands of tons themselves would heft the craft into orbit, but that created a problem. A lot of bombs equals a lot of risk. If you want to avoid killing a lot of people, you have to make sure it's safe and a long way from humanity. Having said that, each launch would be, relatively, not much more polluting than a single early nuclear bomb test. The most incredible thing, though, is that it could actually have been built. Keen for more funding from the military, the team behind Orion designed a missile-armed, bomb-powered battleship and presented it to the Air Force, who eventually bought into the idea. Fairly quickly, though, the US government decided that there was no military purpose for the Orion battleship whatsoever, that they actually had no need for any spacecraft so large and powerful, and that it would put an unnecessary strain on relations with Russia. Which isn't exactly surprising. The project was pretty much dead in the water when nuclear space propulsion was eventually banned by the Partial Test Ban Treaty of 1963. And at number 1, this one is ambitious. Really ambitious. We're talking warp drive. The idea is that you can cheat Einstein's theory of relativity by creating a sort of space-time pressure dip in front of a spacecraft and a wave behind it, pushing the craft along in a bubble, at speeds which, to us mortals, appear faster than light. Mathematically, it works. Mathematically, it's also pretty efficient. Initially, the amount of energy required to form a bubble that could transport a ship across the Milky Way would have been greater than all the energy in the observable universe, which was a problem. But later calculations and streamlining got that down to a ship roughly the size of Voyager 1. Interesting, but purely theoretical, right? Well, not quite, because NASA's Professor Harold White has been trying to warp time in the lab and prove that it can be done. The team are using a device called the Michelson-Morley interferometer, which measures space-time. If one of the legs of the sensor appear even very slightly longer than the other, that's proof that the system works and that the drive is possible. Once you've got that, scaling up is relatively easy. Of course, even if we could build a ship trying to start, steer and most importantly stop something that exists as a bubble within known reality would be quite tricky. But personally, I'd give it a go.